So good morning and welcome to our talk, how to train your dragon and its friends, AI on the edge with the Eclipse Kura. So this presentation will be a journey in the new concept of edge AI, and we'll try to use Eclipse Kura and Eclipse Kapua to deploy machine learning algorithms on the edge. We'll try to also to present a short tutorial for using an anomaly detector based on machine learning deployed on a Raspberry Pi and using Eclipse Kura. But first of all, let's introduce ourselves. The presentation will be held by me, Pierantonio, and Mattia for the tutorial part. We are currently working in Eurotech on ESF, a commercial version of Eclipse Kura. I'm an Eclipse Kura committer since 2015. So, okay, so let's start with some introductory concept regarding the edge AI. So, what is the edge AI? Edge AI is a deployment of machine learning algorithms and artificial intelligence algorithms on the field. So in devices close where the data are located and are collected. It tries to put together the best of two worlds from the edge computing, the fact that you want to process data locally on where the data are produced. Increasing the efficiency, reducing the bandwidth, the network requirements, and improving the latency. Moreover, there are also improvements in data privacy and data security because the data are on the device and are not spread in the net. Regarding AI, we can increase the efficiency and safety of our application in many industries, like manufacturing. For example, for anomaly detection, fault detection, healthcare and logistics, trying to increase efficiency, and also in the smart cities. But this doesn't come for free. So we need to address some challenges. For example, how we can collect data from the field, especially when we have heterogeneous sources. How we can make data available to the user, and how we can manage the fleet of deploying devices. From the AI point of view, we should address the problem regarding how to deploy the models on the edge device and how to protect the more important part of our application, so the AI models. So we think that Eclipse Kura can be a good candidate for apply edge AI concepts in the real world because of its modularity, the fact that it has a lot of drivers that implement different field protocols. It also integrates a lot of IoT cloud platforms, and in particular Eclipse Kapua, that can be used for the device management. And finally, the new integration with the Nvidia Triton Inference Server can enable Eclipse Kura to manage also AI models. So let's start taking a look at the new APIs for managing AI on Eclipse Kura. So Kura 5.1.0 introduced a new set of APIs. For managing inference engines. Inference engines are libraries and services that can be used for managing AI models and machine learning models and allow to perform inference on incoming data. So they don't perform training, but only inference. So we should deploy on the device the already trained model. The first implementations of these new APIs are based on the Nvidia Triton Inference Server. That is a new open source service developed by Nvidia. It enables the user to deploy machine learning. It supports all major frameworks like TensorFlow, TensorRT, and so on. And he also enabled the GPU and CPU acceleration. Kura implements the Triton server providing 3 different components, and that depends on where the Triton server is running. So we have a native service when the Triton server is running on the edge device natively, or we can have the remote service where the Triton server is running somewhere, so on a different laptop, on the cloud, and so on. And also a container service where the Triton server is running in a containerized version on the device or somewhere. And finally, we also added an important features that let's try to protect the models on the device. So in this type of application, one of the most critical and most important part is the model, because we spend a lot of time, a lot of money collecting data, training the model, and then we should deploy in an edge device that is put in the fields. So we leverage the encryption features of Eclipse Kura to encrypt the files and the models in the system. Moreover, we also introduce an AI wire component, so we can put our inference model and run the machine learning algorithm directly on a wire graph, simply connecting to the usual wire graph that Kura provides. For this topic, Mattia will give you some more details during the tutorial. Okay, so what we wanted to show today? We'll try to show you how Kura and Kapua can be used for deploying machine learning algorithms on the fields. So we'll try to cover all the part of a typical machine learning algorithm. So starting from the data collection, we'll use a Raspberry Pi with a Sensat, so a small board that is plugged on the Raspberry Pi for collecting data from different sensors like temperature, light, humidity, and so on. Then we'll put all the data on Kapua, and retrieving data from that, we'll develop a specific machine learning algorithm used for anomaly detection. Once the model is developed and trained, we'll deploy the model again on Kura, and we'll show you how this is possible to detect anomalies and publishing the data again on Kapua. But yeah, first, before starting the tutorial, we need some short introduction on what is an anomaly detection and how this is important for us. Let's say, what is an anomaly? An anomaly is an outlier, so a data that is totally different from the other data we have collected. So a pattern does not conform to a notion of correct behavior of our system. Collecting the anomaly detection is important because the anomalies shows how the system deviates from the correct behavior. So we can, when we have detected it, we can act to recover the correct behavior of our system. So anomaly detection is very useful, very important in different domains like cybersecurity, industry, robotics, for intrusion and fraud detection and fault detection and so on. Typically, there are a lot of algorithms and ways that can be used for detecting anomalies. The classical ones are based on statistical analysis, but in the last years, machine learning has been used successfully for detecting anomalies. Today we will focus on a specific type, the autoencoder, a semi-supervised network that can be successfully used for detecting anomaly in different applications. So, few words on autoencoder. What is an autoencoder? Autoencoder is a specific neural network. It can be used for different type of applications, and we try to use it for detecting anomalies. The goal of the autoencoder is to try to reconstruct the input at the output. is made from an input part. This is an encoder that maps the features in input in a lower dimensional space, so a code, and a decoder that tries to reconstruct the input data starting from the code. When trained, the autoencoder is able to reconstruct normal data, input data. But when you put in the input anomaly, so something that is different from compared to the normal input, the output differs a lot. So we can compute the reconstruction error, and anomalies has an high reconstruction error, and this can be used for detecting outliers. Okay, so let's start the tutorial. The tutorial was developed in Jupyter Notebook. Mattia will talk about that. We uploaded the notebook on this link. You can also take a picture on the QR code and follow all the steps that Mattia will explain for to developing this type of anomaly detector.
Okay, so let's start. First, as Pierantonio said, the Jupyter Notebook is available online. I invite you to use it and try playing around with it while I'm talking, or whenever you want. Everything is uploaded and available. So let's start with the first part about this tutorial, which is setting up the data collection using Kura. As Pierantonio said, we will use a Senset and a Raspberry Pi, and we will to collect the data and put them and push them to the Kapua instance. We will need two abstractions that are available through Kura, which are a Kura driver and a Kura publisher. Kura driver encapsulates all the communication protocol necessary to connect to a field device. In this case, it will be a Senset, as we already said, and the publisher is another abstraction that allows us to publish data in a cloud provider like Kapua. And so let's move on. Let's start with the configuration of the publisher. As you can see here we are in the Kura UI. And as you can see, the connection is already established and available. And this is for time purposes, to save time. So we are now going to create a cloud publisher and give it a name, a meaningful name in the Kura UI. And then we will simply create a new application topic to find our data easier on the Kapua instance. And this is the configuration. Now we will configure the driver, which is here. Here we have already installed through a deployment package all the required software for connecting to the Senset, which is available through, as we already said, a Kura driver. Here we are going to select it and give it a meaningful name, and then create an asset, which is another abstraction available through Kura, which allows us to talk directly to the instance of the Senset. And here we are going to map our channels, which corresponds to our sensor that we have available on the Senset, which will correspond to our feature that we will provide to the autoencoder. Here I'm just creating a meaningful name that we will use to reference the data later in the notebook, and configure it to have to read it correctly. Here we are using an accelerometer. And after applying the changes, you can see that the data are retrieved correctly through the data view. Now we are going to move on with the wiregraph, which is another, which is a low-code environment for setting up application in Kura, which allow for simply connecting reusable components for developing application. In this case, we'll tie everything together from the data collection point of view. So we will have, as we will see, a timer for detecting the sample rate at which we will collect the data from the senset, and the publisher we just created. So here we move to the wire graph view. We will set up a timer, which is called timer because I have a lot of fantasy, and yeah, we'll set it to 1 sample per second, and here you can see that we will select the wire asset we just created, which will not need any additional configuration to work for collecting the data. And finally, the publisher, which will just need to be tied to the instance we configured in the section, in the previous section. So here is the one available. Then we will collect them together, and this will be enough for the data to be published. As you can see, there's a little animation, the arrows, that simplify, makes, dictates the fact that there's actual data running through the connection. So here we are with the cool part, which is the notebook part. Now I will try and switch to the notebook. Yeah, so here is the Kapua instance where we uploaded our data, and we can export everything as a simple CSV file, which will be read by our notebook. Here is the notebook instance that I'm running on my machine. If you want to run everything on Google Colab, following the link that we talked about before, you just need to run this cell here. I don't need to because I already have the. Puoi farmi un shift enter? Shift enter. So yeah, I don't need to run the shell before because I already have the data available on my machine. So let's take a look at our data. Yes. So as you can see, here we have a lot of columns that we are not interested in because, like, timestamp and IDs of the messages are not interesting to the anomaly detection perspective. So we just get rid of it with the feature selection, which is the usual step where we select our feature to be for training our autoencoder on. And then we have our reduced data set composed of accelerometer, gyroscope, humidity, temperature, and pressure sensors. So let's plot the data set. Yeah, a quick disclaimer. As you can see from here, it's a really simple data set that this is a deliberate choice because we wanted to keep things simple, but this approach is generic. This approach will work with any kind of data, and with minimal code changes, you should be able to train a neural network on your data. And yeah. So we now need to perform feature scaling because AI models don't work well with features that have different scales. As you can see, if you run the code there, the accelerometers, yeah, is in ranges between 0 and 1, while the pressure have totally different scales. We will just use a scikit-learn library for that. And as you can see here, now we have a scaled data set. And then finally, we will need to split our data set into a test set and a train set. This will be useful for later. So here we will create our model. As Pierantonio already described, it's an autoencoder has this characteristic hourglass shape with an autoencoder and decoder. We will just use our Keras API. If you scroll down a little bit. Yeah. Here, this will be a simple feed-forward neural network. We will just have, as an input layer, the dimension of the input layer will be the same as the number of features we are using. Then we will go down with the number of neurons, 9 for the first hidden layer, then 6, then 3, and then we'll mirror at the output. Okay, yeah. it's just loaded. Okay, you can see down there, that's the topology of the network. Obviously, if you have a bigger network, you can do this, but yeah. And then we move on with the model training. You can just, you can start it right now so that we can see it in real time. And again, I invite you to, I won't dig deep, into the details of this, of all these parameters. I invite you to try things out on the notebook and see how the model behavior changes upon changing this kind of parameters. And yeah, as you can see here, this is the loss, which is the mean square error, which we are trying to minimize, which is the reconstruction error between the output and the input. So now we can move on to the model evaluation, where I want to give you an intuition on how this autoencoder works under the hood. So, don't worry.
No worry.
Okay. Everything is fine. Yeah. So now we are going to take a sample from the test set and run it on the autoencoder. Here simply I'm calling the predict method of the model. And as you can see here, I'm plotting the data out. In blue, you can see the input data, and in orange, the reconstructed data from the output of the autoencoder. As you can see, it is working fairly well. It's reconstructed correctly the input at the output. This is not really fascinating, I know, but if we move on with the second step, we introduce an anomaly, an artificial anomaly on the same sample we just took. And if we plot the data, we can see pretty clearly that the autoencoder is not able to reconstruct correctly the data at the output. This is because he hasn't seen before that kind of input, or which is the accelerometer set, the z-axis of the accelerometer set to that kind of value. So this is actually working. We have, as you can see, if we can compute the mean square error, we have a much higher value right now. So it is working as expected. And here, I won't cover much into the details about this stuff. This is all needed to have a threshold at which we will trigger the fact that the actual sample is an anomaly or not. So we need to decide when the mean square error is too high and it represents an actual anomaly. Here I'm using the test set and the mean and the standard deviation in the test set to decide whether or not to trigger the anomaly alarm. So now we can move on with the model deployment part, where we need to perform a conversion to run this model on the device on the Triton Inference Server. So we are running this Inference Server in a container on the Raspberry Pi. This is really simply installed by running Docker Pal. So how this model conversion will work? We will split the model into 3 steps, which is the preprocessor model, which will run on the Python backend of Triton, which will perform the steps that we've seen in the data processing section of the notebook, which will be the wire envelope translation, feature selection, and scaling. The second part is the autoencoder, which will be the actual model which just trained in the saved model format from TensorFlow, which will run in the TensorFlow backend from Triton. And then we have the post-processor model, which perform the operation described in the model evaluation part, which is the reconstruction error computation. So everything will be then tied together in an ensemble pipeline, which is a feature by Triton, which will allow us to simplify the handling of everything. So a quick overview of how things works here. Typically, Triton will require you to build a model repository, which is a folder structure composed of the models and the configuration, which, go a little bit up, just to give you an idea. This is a complicated example for giving you an idea of the configuration, but this is a simple protobuf configuration that tells Triton what a model expects at the input, what type of input it expects, what type of output it provides, and if it can be run on the CPU or on the GPU. In this particular instance, we are looking at the ensemble pipeline, which connects all the models together. So it's a little bit more complicated than the other ones, but no worries about that. This is the representation of the configuration in a graphical way. So we have the preprocessor, which expects the 10 features we trained the autoencoder on, and outputs a scaled version of them, and then connects to the autoencoder, which will perform the actual reconstruction. And then we have the post-processor model, which will compare the input of the autoencoder to the output of the autoencoder. The ensemble pipeline will simply perform what we've seen here right now, which means the connection of the three models together, and additionally, it will present the model as a single, the three models as a single one, as we will see later. And the final folder structure, you can see right there. Yeah. As you can see, it's really simple. We have the ensemble pipeline, and which is an empty folder structure because it is simply a configuration. Then post-processor and preprocessor are composed by the configuration and their Python scripts. And then the TensorFlow model, the actual model, which is simply the folder containing the saved model format of the autoencoder. So we can now move on with the actual Kura deployment. So this is the folder structure that we need to move to the edge device, where we will be running the Triton server and the actual inference and Kura. So we can get back to our video. I skipped a lot of seconds. So model deployment, here we go. We are now doing this. We are grabbing the data from the sensor, running them on the autoencoder, and then uploading the results to the Kapua instance. This will be fairly simple, as you will see. The first step we need to perform is the configuration of the Triton component. Here, like a magic trick, I'm trying to show you that the Docker container is not already running. I will create a new Triton server container instance, a container service instance, which, as we talk about, is detected by the fact that we are running the Triton container as a container. We will give it a meaningful name, and then we will need to configure some parameter to make it run. The main one is the image from which we will want to run the container. In this case, is the one I'm writing here right now. Then we need to specify where Triton should be finding the models that we just I just showed you in the folder structure. So in this case, it was on the home Pi directory of the Raspberry Pi. So we will simply put home Pi models. Sorry, it was on the model directory. Then we'll need to provide the models that it needs to make available for clients to use. In this case, they are all the ones that I just showed you. And then an additional configuration for the backend, but I won't give it. It's dictated by the image we decided to use. It's all explained into in more detail in the notebook. As you can see here, we now have our container running. So to publish our data, here we have the Kapua instance that is currently missing the anomaly data. We just need to update the wire graph we had before. It is exactly the same. We just need to add our AI wire component, which will need to be tied together to the instance we configured, and update the model to the one we will use, which is only the pipeline model. As soon as we apply the changes, we should be able to see that on the Kapua instance, we are getting our anomaly data right here and right there. And that's it. This is how we can do all of this from Kura. So, Pierantonio?
Okay. Thanks, Mattia, for the tutorial. As said, we can try the tutorial and the notebook is available at this link. So let's move on. So the first implementation of the Kura APIs for AI was based on the Nvidia Triton Server, but there is a lot of cool tools out there, and a couple of them is the Intel OpenVINO is a library developed by Intel, and is very useful because it supports also some hardware acceleration. Custom hardware acceleration, and also the Eclipse Deep Learning for J. That's an Eclipse project that provides libraries for developing machine learning algorithms. So the idea is to support also these types of backends to increase the support for Eclipse Kura. Of course, any contributions are welcome, and so I think that's it. Thank you. There are questions? We shock us. Yeah.
All the configuration was done on the device. The server is running, the administration server is running on the device.
Yeah, Kura is running on the device also.
So how do you deploy on multiple devices? You can export the configuration.
So the configuration can be deployed using Kapua. So you can connect it to the devices and deploy the configuration. Regarding the models, we can use the deployment service on Kapua. So you can use Kapua for installing and copying the files on each device.
But can you change the configuration for the devices for some?
Yeah, you can do it. In Kura, we have the concept of snapshot. So we can create a snapshot with the configuration and use it for configuring specific types of devices. Other questions? No?
I just wondered, did you look at different models to try to deploy, like robust random cut forest for screening anomaly detection?
I should admit that we have tried only the autoencoder for now, yeah. But Triton Server is able to run a lot of different types of machine learning algorithms because it has a lot of backends. So the TensorFlow, TensorRT, and so on can be used for developing the model and deploy on the field.
Anything that is supported by these backends, it's also supported for this kind of stuff. So everything is available that is available for TensorFlow is available here.
Can you modify the slide with the demo link?
Oh yeah. Also, I think that also the presentation is available somewhere.
Yeah.
Okay. Okay. Okay, so no, not that one. If you are interested on the cover image, so please take a look at this, because also this one is created by the artificial intelligence. Okay, thank you. If you have any more questions or you want further details, we are in the booth 11, the end of the room.